Okay, let's dive right into this. Welcome to our latest explainer. Today, we're taking a pretty fascinating, interconnected journey through the modern clean energy ecosystem. We constantly hear buzzwords thrown around about green power, but honestly, it can be surprisingly tough to see the big picture when the tech is evolving this rapidly. So our goal today is to map out exactly how this ecosystem functions in the real world, looking at the entire pipeline. We're going to trace the journey from the raw environmental sources that surround us every single day, all the way to their final global impact on our society and our economy.
Here is our roadmap for today. 1. The renewable energy sources. 2. Conversion and efficiency measures. 3. Policy support for deployment. And 4. Economic and environmental impacts.
Before we can even talk about the solutions, we kind of have to start at the very beginning of our clean energy journey. It's a simple question, but a profoundly complex one. Where does our power actually originate? Think about it. When you flip a switch, are you harnessing the gravitational pull of the moon on our tides or the nuclear fusion of our sun? Understanding the sheer scale of the physics at play is absolutely the first step in understanding how we transition an entire global economy away from buried hydrocarbons.
All right, let's jump into section 1, the renewable energy sources, or the power generators.
Now, what's really interesting about this slide is that it shows we aren't just relying on a single magic bullet to power the future. The core 5, solar, wind, hydro, biomass, and geothermal, represent a highly diversified energy portfolio. And that diversity, it's the absolute secret to grid stability. Solar and wind are highly visible, sure, but they're inherently intermittent. The sun eventually sets and the wind dies down. That is exactly where geothermal and hydro come into play. They provide the immense, consistent baseload power required to keep an entire global power grid perfectly stable and humming without ever needing to fall back on finite fossil fuels. It's an intricate, global balancing act of natural forces working right in tandem. Take biomass, for example. It's not just about, burning wood, it's really about closing the carbon loop. By strategically utilizing agricultural residue or municipal waste, biomass turns our inevitable societal output back into dispatchable, on-demand energy. This just proves that renewables can elegantly utilize biological, real-time carbon cycles, not just rely on high-tech solar arrays or massive concrete dams. It's a completely dynamic approach to managing the biological resources we already have on hand, literally transforming waste streams directly into grid stability.
But here's the catch. We have this incredible bounty of natural energy all around us. But a gust of wind can't directly charge your laptop, and the heat of the earth can't run a server farm without an intermediary. Bridging that gap between raw natural forces and the device in your hand requires immense, precise engineering. So how do we actually optimize this raw power so it's useful to modern human society?
Which brings us to section 2, conversion and efficiency measures. This is all about maximizing the output. Energy conversion is where raw physics meets human engineering. It's the incredibly complex mechanical and electrical translation process that makes modern life possible. We're talking about the aerodynamic innovations carved into next-generation turbine blades, or pushing the extreme thermodynamic efficiency limits of photovoltaic cells using advanced semiconductors. This conversion tech dictates exactly how much of that raw environmental energy we can successfully capture and translate into a usable alternating or direct current. The better the engineering, the more power we extract from the exact same environmental footprint. Let's move to this and see how this builds into a highly sequential 3-step pipeline. Step 1, renewable generation, captures the raw force of nature. Step 2, energy conversion technologies, translates that force into an electrical current. But crucially, Step 3, energy efficiency measures, is the final phase that ensures our bucket isn't leaking. Once we've done the incredibly hard, expensive work of generating and converting the power, we absolutely must ensure the end systems using it are operating at peak performance. Because honestly, efficiency is the ultimate safeguard of this entire ecosystem. This includes smart grid technologies utilizing AI to perfectly route power during peak demand, or next-generation insulation materials in commercial real estate that drastically reduce heating and cooling loads. Think about industrial manufacturing plants recovering waste heat just to power their own secondary processes. Implementing these specific efficiency strategies isn't just some afterthought, it's mandatory. After all, the absolute cheapest and cleanest megawatt is the one we never have to generate in the first place.
Okay, so we've covered the natural sources and we've covered the brilliant technology that converts and optimizes them. But technology alone doesn't change the world. It has to be built, funded, regulated, and integrated into complex societies. So what actually drives the massive deployment of these systems on a global scale?
That leads us right into Section 3, Policy Support for Deployment, which acts as the catalyst.
So, the crucial point is that without structured policy support, even the most groundbreaking technology struggles to scale in a legacy market. Policy acts as the necessary catalyst to level the playing field. It comes in the form of feed-in tariffs or aggressive tax credits that de-risk early-stage investments for private capital. It's renewable portfolio standards, requiring legacy utility companies to hit strict clean energy quotas by a very specific deadline. And it's massive federal-level infrastructure grants designed to modernize our aging transmission lines. Basically, policy is the societal blueprint that bridges the gap between a great engineering concept in a laboratory and widespread, everyday deployment.
And finally, Section 4, Economic and Environmental Impacts, the ultimate outcome. And this brilliantly illustrates how this massive global shift produces a profound dual outcome. Economically, we're witnessing a massive wealth transfer into entirely new advanced manufacturing sectors and a historical decoupling of GDP growth from fossil fuel reliance. We are literally talking about millions of high-paying jobs in retrofitting and grid management. Environmentally, the dividend is immediate and tangible: aggressive decarbonization, massively improved urban air quality, and the reclaiming of habitats previously lost to extraction. The clean energy transition isn't just about changing how we plug things in, it is a simultaneous rewiring of both global financial markets and the Earth's biosphere. So as generation technologies get cheaper and our global policies get bolder, the fundamental question isn't just if we can power the world cleanly, but how we're going to manage an era of potential energy abundance. Will clean power solve our historical geopolitical tensions, or will it create entirely new ones around the critical minerals needed to build this new infrastructure? That is for sure the next great frontier. Thank you so much for joining me on this explainer, and keep questioning how the world around you is powered.